when we consider cycloalkanes, if we draw them in 2 dimensions, that's okay, but we have to remember that they don't really exist in 3 dimensions. They sort of twist a little bit because if they were to remain flat, they will experience considerable angle strain, right? That eclipse, forced eclipse formation that we would put them if they were flat or in 2 dimensions. Um, they will also experience torsional strain. Now, when we talk about angle strain, that's a little bit different. Angle strain is whenever you deviate from the ideal sp3 hybridized angle of 109.5. You can see here we have different angles from 60 degrees at your 3-member ring, your triangle, all the way to 135 at your 8 carbon system. There is one that is a little bit optimum compared to everybody else, and we can analyze that by doing calorimetric or combustion analysis. Looking at the data, the 6-member ring is the most stable ring size. It has the lowest energy per methyl group. You can see here considerably less than everybody else. So that would be one of the most stable ring systems that we will find in nature. Cyclobutane is 27 kilojoules per mole, less stable than cyclohexane per methyl group. It has an angle strain, a bond angle of 88 degrees. That's pretty far away from 109.5. It has slight torsional strain because adjacent carbon-hydrogen bonds are neither fully eclipsed nor fully staggered. Moving on to cyclopentane, you have more carbon atoms forming that ring, so you have a little bit more freedom. The consequence is that cyclopentane is only 5 kilojoules per mole less stable than cyclohexane per methyl group. Very little angle strain. You're almost at that 109.5 degree ideal angle. I think it's 108. Slight torsional strain. It actually twists into what we call an envelope conformation. You can see here uh, these 3 carbon atoms, they sort of move upward outside of the angle of the entire or the plane of that cyclic structure. That actually makes it a little bit more stable than if it remained flat. Cyclohexane, on the other hand, can adopt a variety of conformations. That actually is a very advantageous trait. Out of all of these, the share conformation is going to be the one that is most stable by far. These are the ones here. That's that hexagon-like structure, so one of the peaks sort of move upwards, the opposite side moves downwards, simulating what we will call a share. You can also have a both conformation, and then you have shares and you twist both conformations with their respective energies. Cyclohexane has no ring strain when it is in share conformation. It has no angle strain, and it has no torsional strain either. So that means that this sort of conformation that it adopts is very, very advantageous in terms of energy. The other possible conformations of cyclohexane have some amount of angle or torsional strain or ring strain. If you look down here and here, this is what the Newman projection for your cyclohexane in share conformation will look like. Here we have some simple instructions on how to draw cyclohexane in a share conformation. Um, if you want to follow them, that's fine. If you have a different way of doing it, so long as you arrive at the same structure, that's perfectly okay. If drawn correctly, the shear conformation should contain 3 sets of parallel lines. So these two are parallel, these two are parallel, so are these two. Now when you have that, this is important because now we can start looking at the substituents, whether they are hydrogen or something else. One of the substituents in each of the carbon atom, you're going to have 2. One of them is going to be in axial position, the other one's going to be in equatorial position. So axial positions, the one in red here, they refer to an axis that is perpendicular to the shear conformation, so up and down. Equatorial, they are parallel to the plane of the ring, so they're sort of like an equator, right? That's where the name comes from, so side to side. So these are the ones in blue. As you can see, this carbon atom has one axial, one equatorial, and the same is true for every carbon atom in that structure. Adding the axial substituents is easy, just point up and down, alternating them. The equatorial are a little bit less obvious. They are drawn off the ring and they run parallel to the lines in the shear. So we have these two parallel to these two. These two are parallel here, and these two are parallel here. And once you put everything together, this is what your structure should look like. My cyclohexane has one substituent. There are two possible shear conformations, axial and equatorial. Ring flipping happens by rotating the carbon-carbon bonds in the ring. Axial substituents become equatorial and vice versa. Sort of like turning it inside out, so to speak. Now this is all hypothetical on the pencil, right? Um, the ring in nature doesn't turn upside down on its own. Consider methyl cyclohexane, for example. The shear conformation, where the methyl group is equatorial, is the more stable shear. So much so that 95% of the molecules that you will find are in that position. The reason for that is that you have the biggest separation, less steric interactions, less steric hindrance. So overall, less repulsion. At room temperature, methyl cyclohexane will be in the more stable shear for the immense majority of the time. In the axial position, the methyl group causes steric interactions, so repulsions. The steric strain from a substituent being in the axial position is the result of the 1,3 diaxial interactions. So these are repulsion interactions. These actually increase the overall energy of your molecule. The 1,3 diaxial interactions are actually gauge interactions, which are not present when the methyl group is equatorial. So removing that interaction actually makes your system more stable, which is why for methyl cyclohexane, that is the preferred position. Larger groups will cause more steric hindrance. Steric hindrance is a type of repulsion that you get from just being a large molecule with a bunch of electrons um, interacting with other groups, right? That repulsion that you get. And as you can see, the larger the group, the bigger the 1,3 diaxial interaction becomes. Now, when we have dye substitution, two substituents, solid or dot wedges are used to show positioning of the groups on the ring. So you can do this. You have methyl group and you have chlorine. So chlorine is up, is coming towards us. That's why we have a solid wedge, whereas a dash wedge is away from us, behind the screen, so to speak. So you can translate that into this structure right here or into this structure right here. It really depends on the context, what information you're looking to get out of the system. Now here, let's try practicing both shear conformations of the di-substituted cyclohexane. Now here, they're not next to each other. There's actually a carbon in between them. So 1,3 positions. We have a methyl group and an ethyl group. Methyl group contains one carbon atom. Ethyl group contains two carbon atoms. So first draw the shear by labeling the substituted carbons in the given structure. Then we translate. This is actually, for me personally, is one of the easiest ways. I sort of answer all the questions first, then I go back and I switch the conformation or the drawing style. So you can draw a hexagon. Your methyl group is in position 1, your methyl group is in position 3. Now I draw the shear, position 1 versus position 3. Axial positions, they're going to be up. If you were in position 2, it would be down, then up. So methyl group has to be in an equatorial position because otherwise it would be up, according to the system we had set up a few slides ago. So that tells me that in position 1, 3, when they are in different sort of wedge dash conformation, then one of them has to be axial, the other one has to be equatorial. Now what would be the other option? The other option would be to switch these two. Ethyl would be equatorial, methyl would be axial. That would be sort of a ring flip, so to speak, which is what we see here. To draw the other possible shear, we must make sure that the ethyl group will be equatorial, methyl group will be axial, like we just said. Now, out of these two, which one would you expect to be more stable and why? Well, here, the group that is in the equatorial position would be the one with the least amount of steric hindrance or causing the least amount of steric hindrance to the system. I would expect the larger group to be as far away as possible for the system to be more stable. Ethyl is more is larger than metal, right? Two carbons versus one carbon. So I would expect the one on the right to be more stable because of that reason I just mentioned. Now let's talk a little bit about cis and trans isomers. When naming a disubstituted cycloalkane, we use the prefix cis when there are two groups on the same side of the ring, or trans when they are transversal or in opposite planes, uh, opposite sides of a ring. So this would be a cis isomer versus a trans isomer. They look the same, they look very similar, but when you're in a ring system, you can't really rotate between one and the other. That also happens when you have a double bond, for example. And because you can do that, then they are stuck in either cis or trans position, and that is something that we need to be able to identify properly. Each compound exists as two equilibrating chairs, spending more time in the more stable chair conformation, so either the equatorial positions or the axial positions. Now let's talk a little bit just briefly about polycyclic systems. We have here, for instance, decalin, that is a two six-member rings that have been fused together. The decalin structure is found in many natural occurring compounds, such as in steroids. Steroids, this is one of their structure, the four rings that we see here. And this will be the decalin right here in the middle. This is testosterone, just one of the steroids that we see in nature. And you can go from this type of structure with your solid wedge and your dash to your chair type conformation with your axial and equatorial. There are many important structures that result when more than one ring is fused together. We have camphor, camphene, among others, right? These are fragrant products, and we use them all the time. So it's important that we know how to draw them, how to describe them in terms of their structure. And for instance, diamond, that will be one of the more, let's say, famous polycyclic systems. This is just a network of six member rings, all of them fused together. And this is what that would look like.